real exponential signals. A continuous time real exponential signal is expressed as x of t equal to a into e power alpha t, where a and alpha are real values and are constants. Here in this equation, if alpha equal to 0, then the value of x of t is a. It represents the amplitude or value of signal over the entire time axis is a constant and its value is equal to a. Therefore, the signal, since the amplitude of the signal is constant over the entire time axis, the signal is represented as a DC signal. Therefore, we can call it is a DC signal with infinite fundamental period and 0 fundamental frequency. Here in equation 1, if alpha is greater than 0, then the signal becomes x of t equal to a into e power alpha t, where the signal is expressed as an exponentially rising signal. Some examples of exponential rising signals are current through a diode, forward current through a diode, response of a RC low pass circuit. If alpha equal to 0 in equation 1, since alpha is a negative value, then equation 1 becomes x of t equal to a into e power minus alpha t, represents an exponentially decaying signal as shown in the figure. The example for exponential decaying signal is response of an RC high pass circuit. Next, complex exponential signals. Here a complex exponential signal is expressed as x of t equal to a into e power st, where s is a complex variable and is defined as sigma plus j omega. Therefore, equation 1, substituting s value in equation 1, the signal x of t is expressed as a into e power sigma plus j omega into t. According to the algebraic relation a power m plus n equal to a power m into a power n, equation 1 is expressed as a into e power sigma t into e power j omega t, where sigma is the attenuation constant and omega is the angular frequency. Here, according to the Euler's formula, e power j omega t is expressed as cos omega t plus j sin omega t. Therefore, equation 2 is becomes x of t equal to a into e power alpha t of cos omega t plus j sin omega t. Here, considering case 1, if sigma equal to 0, then equation a becomes a into cos omega t plus j sin omega t, which is, that means the signal x of t is a constant sinusoidal signal or a sinusoidal signal with constant amplitude as shown in the figure. Such waveforms we call it as sustained oscillations, which are generated by the generator or oscillator circuit. Here in equation 2, in equation 4, if sigma is greater than 0, then the signal x of t becomes a into e power sigma t into cos omega t plus j sin omega t. The signal x of t is a sinusoidal signal whose amplitude is growing exponentially. Therefore, it is a exponentially overdamped signal. If sigma is less than 0, a negative value, then equation 4 becomes e into e power minus sigma t into cos omega t plus j sin omega t. The signal x of t is a sinusoidal signal multiplied by a exponentially decaying signal. Therefore, it is a underdamped signal. Next, impulse signal. Here the impulse signal has an infinite magnitude and time at a 0 time period with an area a. Here the this figure representing an impulse signal, it is denoted by delta of t. Therefore, according to this graphical representation, the impulse signal existing at time t greater than 0 and at time t equal to 0 and at time t greater than 0 and t less than 0, its value is 0. In this impulse signal also referred as Dirac delta function, and its functional representation is expressed as delta of t equal to infinite at t equal to 0 and its value is 0 at time t not equal to 0. Here, if the magnitude of the impulse signal is considered as 1, then the impulse signal is referred as unit impulse signal. Um, Unit impulse signal, and also the total area covered by the unit impulse signal is unity. Therefore, integral minus infinite plus infinite delta of the dt value is equal to 1. Here, if this impulse signal is delayed by m units of time, the delayed unit impulse signal is expressed as delta of t minus m. Here, delta of t minus m is equal to infinite at t equal to m and 0 at t not equal to m. Here, this figure represents a 1 unit left shifted unit impulse signal, and this figure represents a 1 unit right shifted unit impulse signal. The next step signal, it is denoted by u of t, and here according to this graphical representation, here the amplitude of this step signal is 0 at time t less than 0 and at time t equal to 0 and t greater than 0, its amplitude a constant that is equal to step size of the signal. Therefore, its functional representation is u of t equal to a at t greater than or equal to 0 and 0 at t less than 0. If the height of the step is equal to 1, the unit step signal is referred as unit step signal. U of t equal to 1 for t greater than or equal to 0 and 0 for t less than 0. If this unit step signal is delayed by m units, it is expressed as u of t minus m and its value is 1 for t greater than or equal to 1 m and 0 for t less than m. Here this unit step signal is a left shifted 1 unit left shifted unit step signal expressed as u of t plus 1, and this unit step signal is a right shifted 1 unit right shifted unit step signal expressed as u of t minus 1. Ramp signal, it is denoted by r of t, and here the as time increases the amplitude increases linearly. Therefore, the slope of the line is a. Therefore, the ramp signal functional representation is r of t equal to at for t greater than or equal to 0 and 0 for t less than 0. Here in this equation, a represents the slope of the line, and if a equal to 1, that means slope of the line is 1, then the ramp signal is expressed as unit ramp signal, and its function representation is r of t equal to t for t greater than or equal to 0 and 0 for t less than 0. And here the relationship between a unit step signal and ramp signal is expressed as r of t equal to t into u of t. Parabolic signal. Here the parabolic signal is denoted by p of t. As t greater than 0, the curve represents a parabolic curve, and it is defined as p of t equal to a into t square by 2 for t greater than or equal to 0 and 0 for t less than 0. Here, if constant a equal to 1, the parabolic signal is referred as unit parabolic signal, and p of t equal to t square by 2 for t greater than or equal to 0 and 0 for t less than 0. The relationship between ramp signal and parabolic signal is p of t equal to the relationship between unit step signal and parabolic signal is p of t equal to t square by 2 into u of t. Here one important relation is parabolic signal is expressed as p of t equal to t square by 2 into t square by 2 into u of t. Differentiating the parabolic signal results a ramp signal. T square by 2, differentiation of t square by 2 is 2t by 2. 2 to cancel t. Here the differentiation of parabol ramp signal results a unit step signal, and the differentiation of unit step signal results a impulse. And here in the other way, the integration of impulse signal results step signal, and the integration of step signal results ramp signal, and the integration of ramp signal results parabolic signal. Next is rectangular function. The rectangular function or the rectangular pulse is denoted by rect of t or pi of t, and its amplitude is 1 over a duration minus t by 2 to plus t by 2. And here in functional representation, pi of t equal to a for modulus of t less than or equal to t by 2, and 0 for modulus of t greater than t by 2. And here this rectangular pulse can be obtained by using the unit step signals, and is expressed as pi of t equal to u of t plus 1 by 2 minus u of t minus t by 2. Here combining the unit step signal started from t equal to minus 2 and from t equal to plus 1 by 2, a rectangular pulse is obtained. And here this figure represents a 2 units left shifted, or 1 unit left shifted rectangular pulse, and it represents a 1 unit right shifted rectangular pulse. Next, triangular pulse. The triangular pulse denoted by delta of t, and here its amplitude is actually it is a combination of a increasing ramp function and a decreasing ramp function. Now this functional representation is delta of t equal to 1 minus modulus of t by a, where modulus of t is less than or equal to a, and 0 for modulus of t greater than a. Here this figure represents a right shifted unit step signal, and it represents a left shifted triangular pulse. Here the functional representation of the triangular pulse is expressed as by using line equation. The functional representation of this triangular pulse can be obtained. Therefore the equation of line is x minus x1 by x2 minus x1 equal to y minus y1 by y2 minus y1. And here from the figure, the coordinates at time t equal to minus 2 are x1 y1 equal to minus 2 0, and at time t equal to minus 1 the coordinates are x2 y2, they are minus 1 and 1, and x and y are x-axis time t and y-axis delta of t. Here substituting all these values in equation 1, then the equation for delta of t, that means the going ramp function equation, becomes delta of t equal to 2 plus t for t ranging from minus 2 to minus 1. And here now considering the decreasing ramp function, the coordinates at t equal to minus 1 are x1 y1 equal to minus 1 plus and 1, and x2 y2 at the coordinates at time t equal to 0 are x2 y2, and the coordinates are 0 0, and x comma y are t and delta of t. Therefore substituting these values in equation 1, then we have delta of t equal to minus t, where t is ranging from minus 1 to 0. Therefore combining equation 2 and 3, the functional representation of this triangular pulse is delta of t equal to 2 plus t for t minus 1 to minus 2 to minus 1, and delta of t equal to minus t, where t ranging from minus 1 to 0. Sinc function, it is denoted by sinc of t. Here this sinc function oscillates with a period of 2 pi and decays exponential with increasing t. Actually the sinc function form is The functional representation of this sinc function is sinc of t equal to sin t by t, where t ranging from minus infinite to plus infinite. It is a even function of t. The next function is signum function. It is defined as the sign of the independent variable. Yeah, it is denoted by signum function. Sgn of t represents signum function. Here this signum function defines the sign of the independent variable t. Here the functional representation is Sgn of t equal to -1 for t less than 0 and 0 for t equal to 0 and equal to 1 for t greater than 0. And here in using unit step functions, this signum function is defined as Sgn of t equal to u of t minus u of minus t. That means it is the difference of a unit step function and its time reversed version. This signum function is used in the communications and control theory. Gaussian function, it is denoted by g of t. Here this curve represents bell-shaped curve. Bell-shaped curve, it is defined as g of t equal to e power minus a into t square, t ranging from minus infinite to plus infinite.